Okay, so our last topic today is on thermodynamics, and as I've shared with you guys a few times before, I like it, in a certain way. It's very similar. I always introduce a new concept, and then I introduce a new formula. It's very, very similar there. I really want to point out again, though, if you're not great at the math part of the formula, that's fine. It's not the end of the world. That's not all that makes physics physics. I'm about to teach some quantum physics to my grade 12s today. There's no math formulas. We just don't care about the math. We just care about the understanding of concepts. But you can't do the math equations. That doesn't mean you should give up on physics. It's fine. It's actually okay. That tracking software lab, because I really want to point out that physicists don't just sit around and just do math equations all day. We have computers, right? We have computer technology to do all the math for us. You should still practice that while your brains are developing, right? While you guys are in high school, we should do some practice on that. Anyways, I was getting off topic. So we're going to start this lesson today with the same thing. I'm going to introduce a concept of thermodynamics, and then we're going to finish with one more formula of math examples. Okay? And I want to begin with basically where we actually started physics. Do you guys remember what the definition of physics is? What makes something physics? What are we studying in physics? Anybody? Work isn't bad. That'll work. And what else, though? Energy plus what? Plus matter. Okay. What's chemistry all about? Matter. What's physics all about? Take that matter and give it some energy, and now it does something. Okay. We started our unit on physics discussing what energy is. And energy is one of the single hardest things to discuss. It is such an abstract concept. Bottle is, I could point to one and I could draw you a water bottle, right? To ask you what the color red is. As long as you can see, I can give you an example of that. Energy is a very abstract concept. Just put it in your hand. Can you really do that? Matter is stuff, but energy is this thing that causes the stuff to move. Years and years ago, scientists thought that energy was some sort of magical molecule that certain things had. And so if fire burst out of a log, they thought that logs had more of this caloric stuff. And they thought that that was energy. They were horribly wrong, but about what energy is. And honestly, even to this day, the best definition that scientists have for energy is that energy lets us do work. And then what makes it really frustrating is, what's the definition of work? Work is anything that uses up energy. Doesn't that seem so stupid? That the two definitions are basically they lead back to each other? Because it's this concept that we can't really tangibly discuss, right? It's this idea of energy. Okay. Now with that in mind, then let's talk about machines. Okay. We know that machines have the ability to do work, and we know that energy basically lets you do work. And we would love to make machines that are basically perfect consumers of energy. They don't waste anything. And here's my start of the lesson here. Most cars are now powered with gasoline. And ideally, we'd like all of the energy in the gasoline to transform into motion. Because isn't that the work that a car is supposed to do? A car is supposed to take gasoline, chemical energy, and it's supposed to make the car move. But 33% of is actually wasted due to heat. It doesn't actually make the car move. It causes it to heat up. That's why cars have different components to help them cool themselves back down. Otherwise, a car gets too warm and it overheats, right? That's why we have coolants and radiators and oil and lubrication to help with that, right? So that kind of leads to my first question here. Well, why is so much heat generated? And ultimately, this is probably one of the biggest reasons why. Friction. As there are moving parts in a vehicle, as a piston goes up and down, as things spin around in circles, as surfaces rub next to each other, friction is given off. It naturally will be. And so heat is bound to be generated. What are engine designers doing nowadays to try to reduce the amount of heat? Anybody watch Elon Musk's big reveal a couple days ago? Anyone see that video? Most everybody's nodding here. Bulletproof glass that's not overly bulletproof. So if you haven't seen this video, by the way, just in case you're not in on the context, Tesla the car company recently did a big unveiling of the Pro. Kind of looks like a really bad version of the Batmobile, if you ask me. Like, it was really interesting shape. Anyways, that's not here or there. And it was hammered the doors and said that threw like a ball at the window, but the window shattered, and it was kind of embarrassing. Anyways, that's not what different about how engines work. Rather than having engines that have moving parts that are based on like combustion and controlled explosions, Tesla's trying to make a car that's run off of a battery. Does that make sense? Now the battery, I want to discuss that for a little bit here. In Alberta especially, some people might say, oh, electric cars, it's better because it uses like it's better, you know, it's not using fossil fuels. That's actually a complete lie right now though, because when you plug your Tesla in to the power system, where does the electricity ultimately come from? Probably natural gas that's been burned. However, even plugging in an electric car and you're still ultimately probably using fossil fuels as its ultimate source, what's better about Teslas is they're way more energy efficient. So even though they do get their source from burning natural gas in Alberta, sometimes wind power, by the way, a little bit of wind in Alberta, but we don't really have nuclear power in Alberta. We don't have hydroelectric power in Alberta. So most energy still comes from fossil fuels. So if you're driving a Tesla, you're still burning fossil fuels, but you're more efficient about it because a Tesla doesn't have that 33% wasted due to heat because it's using a battery. Right? And so the motor that you have in a Tesla is different than the motor than you have in an internal combustion engine because you don't have to have all of those explosions as pistons go up and down and up and down. Me is what's going to be the main revolution in the 21st century. Okay. We can actually look back at history, and it's kind of cool, but there has been an advent in technology in each of the last 3 centuries in terms of transportation. In the 1800s, which is the 19th century, the steam engine was developed, and that allowed there to be trains for transport. 1800s, which is the 20th century, Henry Ford figured out how to basically mass produce automobiles, cars for the first. Of the 21st century, which is the 2000s, right? I think it's eventually going to be the electric vehicle. Off of fossil fuels entirely, they won't necessarily be more efficient. Does that make sense? And that's our goal today, is we want to talk about efficiency and where that energy transfers. So to begin with, I want to introduce to you to the 2 laws of thermodynamics. These are rules that we seem to have discovered over the last number of centuries that are regarding energy and heat. And I'm going to give them to you in like their official words, and then I'm going to try to give you some analogies to help understand them better. Thermodynamics states that the total energy, including your heat in the system, has to remain constant. This is often known as the conservation law. What it basically says is that whatever energy that there is, that's what we've got. You can't make more, you can't have less. You can't lose energy. Not that you can like put energy on a scale and say, here's some energy, because it's not an actual thing, but you can't just make energy out of nothing, right? I can't just magically have energy show up, but I can't lose it as well. There's a consistent amount. There's a total that we have, and it's very similar to the law of conservation of mass. I think we played with Lego blocks at some point, and I gave you some Lego pieces, and I said, here, take these Lego pieces, rearrange them, make something new. If you started with 5 Lego pieces, you have to have one disappear. That breaks the law of conservation of mass. Same thing with energy. If before something happens, you have 100 joules of energy, by the time you're done, you better still have 100 joules. Okay? That's the first law of thermodynamics. What I'd like to do before I show you the second law of thermodynamics is to introduce the concept of what's called a perpetual motion machine. And these are machines that mostly were trying to be designed in the 17, 18, 1900s probably, where they were machines that would run for forever. Where once you start this machine, it keeps going to infinity. And you can kind of see in these pictures here that that's just not logical. Imagine that here's a cup that's got like a funnel. And, so normally this water would fall through the funnel. And normally if like the tube went down like this, it would drain, right? But what if you took the funnel and you basically sent it right back up to the top like it is right here? Does it make logical sense to you that water would then flow down through here, go back uphill against a gravity, and just kind of cycle like that? Like, that doesn't really make sense. But that's basically what a perpetual motion machine would do, is that once the water starts moving, it would just keep going in a circle for forever. It would never stop. Here's maybe a better picture of a hypothetical device so you can see how this works. I'm just going to pick a random spot to start. Here's turns right here. It causes this thing to rotate, which causes this to rotate, causes this thing to rotate here, causes this thing to rotate here, causes this thing to rotate here, which makes this one rotate again. You see how it's kind of like a loop, where A causes B to happen, B causes C to happen, but then you get back to the start again. Here's A causes B, B causes C, C causes D, D causes A, and the theory would be this would just run for forever. Keep going till infinity and never stop? I think you probably all recognize that. That's not logical. And that's because of the second law of thermodynamics. Okay. Now, the second law is, it's kind of wordy, so I'm going to give you some analogies in real life to help illustrate them in a second, but here's the words of the second law. It says that heat naturally has to flow from a hot object to a cold one, never from cold to hot. Okay. First, let me describe that law again. What is heat? Heat is molecules that, when heat transfers from one into this molecule, which bumps into this one, and that's how heat is transferred. So heat has to cold objects. Okay, when you're out, say some gloves, and you're wearing a toque and you're wearing your coat, why are you wearing that? Is it to protect you from the cold? Sometimes we say that. We say that the right physics way of thinking about it. Does that make sense? Like, there is no such thing as cold. There is no cold outside that is hurting you. What's actually happening is your body is losing heat to the surroundings as the, finger quotes here, as the cold air, these natural vibrations transfer to the surroundings, and you vibrate less quickly. When you vibrate less quickly, you feel cold. But it's not like you're actually feeling cold hit you. You're actually feeling the loss of energy leave your body. It's why wearing a hat when you're doing like winter camping is really important. Your head is a good place for heat to be lost from. So if you can wear a toque or a hat, then it prevents heat loss, especially if you live, like, say, in really northern climates. Does that concept make sense there? Well, that's the second law of thermodynamics. It basically states that hot objects, I guarantee you, there is no way to solve this problem. Hot objects will always lose their heat to lower temperature objects. I guarantee it. You cannot build me a thermos so good that it won't lose some heat over time. It might take 15 years, but I guarantee you cannot build me an insulated thermos so good that, like, the boiling hot chocolate that I put inside of it won't eventually cool down. Does that make sense? That's the second law of thermodynamics. Now let me put them in different words for you here. I like the analogy of going to Vegas and gambling, if that's okay. So here's the first rule in a Vegas analogy. You go to Vegas with $100. You may come out ahead a little bit. You may come out a little bit behind. So you went with $100. Maybe you walk out with $100. And you managed to win a couple of games of blackjack. Cool. But did you really get free money? You didn't just make money out of nowhere. It came from somewhere. And let's say that $100 may the money, or did it just get transferred to someone else? Conservation. You can't make more energy out of nowhere. It has to come from somewhere. You can't use energy. You can't have energy just escape from nowhere. It has to go. There is a set amount of energy. That's rule one. Is that if you're still in Vegas, although it's nice to think that you can maybe come up, the truth is, you ever heard the phrase in Vegas, the house always wins? You ever heard that phrase? The way that Vegas is set up is that all of the games you play, like craps and blackjack and dominoes and roulette, they're all set up so that in the long term, Vegas always wins. They might not win every single hand, but long term they do. And that's a good way of putting this, is that imagine that you have 100, let's call it joules, because that's the energy unit to start with, I guarantee you that over time, if you want to accomplish something and like say have 99 joules worth of work done, there is always going to be 1 joule of waste or of loss. And in that same gambling analogy, you might like to long term, you will definitely lose money. Efficiencies. The games that you play in Vegas are rigged. If you didn't know that, this is entirely another lesson here. Long term, you'll always lose a little bit. If you have some heat input and you try to do some work, 99 out of 100 was useful, but there's definitely going to be something that escapes. You understand that concept there? Right? So even like the most insulated system that you would think is going to be perfectly efficient, this law basically is all about efficiency. Maybe that's a better way of putting it. Efficiency. Basically what the second law of thermodynamics states is that you cannot have a 100% efficient device. It's impossible. You can't walk into Vegas with $100. It won't happen. A little bit. It's for the first 2 laws of thermodynamics. So 1 basically states you're not going to come out ahead. You can't win. You can't start with 100 and get to 102. And you can't start with 100 and lose down to 98. Like that 2 that you lost, it went somewhere. And not only can you not come out ahead, the first rule, but the second rule is I guarantee you're going to lose something over time. Well, that leads to our, before I get to that, you might actually argue, you might say, Chris, hang on, what about air conditioners? This rule here says that heat always goes from hot to cold, right? That's what the rule says. You might argue, Chris, how does an air conditioner work then? Well, you can make things go from cold to hot if you do work to do it. You ever seen one of these air conditioners here, just like a portable one? You guys know how these work? You might be standing right here, feeling what you perceive to be cold air coming out of right here. But it's not like it's made cold air out of nothing. All it does is it pumps the hot air out the back. Okay. Melissa and I still remember this story. We were on our honeymoon. This was 10 years ago. And we were at a small little hotel kind of thing. I think it was in Radium, BC. And inside the lobby, the gentleman has one of these air conditioners sitting right there with the cold air blowing right on his face. But rather than pumping the hot air into the outside, he had just left the tube around the back just sitting there. Now, he was feeling cold air because the cold air was pumping on him. But just as much hot air was actually just getting pumped back into the room. Was the actual room cooling down? No, because that would be breaking the first law of thermodynamics. There is only so much energy to go around. If you want to pump more on the outside, then there's less on the inside. But if you pump the hot air and it still stays inside the room, nothing really will happen, right? But, I mean, would you feel cold air over here? Sure. But the exact same amount of difference, this person over here would feel hot air. So, yes, you can kind of make cold air work, but it's like... So then this is really the core then of what we're going to do math-wise. We want energy-efficient devices. We'd like to make it so that when energy, we know we can't just get there, but at the very least, we'd like to prevent loss. And one of the best examples I can give for that is light bulbs. Okay, these light bulbs that are in the classroom here, they're some of the fancier, newer ones. What's the main goal of a light? Light. But you know what light bulbs also sometimes produce? Heat. A little bit. That means that they're thermodynamic. Efficiency. We would like to put in electricity and get that wasted energy. There's always that loss due to heat or sound or something else, right? Them over time. It's a fairly simple formula, though, in order to figure out how efficient they are. I don't even ever write the formula down on the board because efficiency is basically the same formula you'd use for a percentage on a test. If I were to say that you got, calculate that as a percentage, right? You just do 18 divided by 30 and you times by 100. Efficiency is how much output you get divided by input. And based on the first, that the output is a lower number than the input. The output has to be lower, the input has to be higher. You always have to do small divided by big. Because what would happen if you tried to do 30 divided by 18? What would you get as a percentage? Over 100, right? Can you get over 100? No, because that would break which law? The first law. The first law says you can't have over 100. I guarantee you it's less than 100%. You can't be perfectly efficient. Something will be lost over time. And so I'm going to do two examples here, and that's actually it for not only our lesson, but that's it for our unit on physics. Okay? And I think you'll find these examples to be fairly straightforward. Maybe I'll leave this slide up for a bit. The concept is you just take the output, divide by the input. So, for example, if you had 18 joules of output energy, 30 joules of input energy, how much energy was lost? How much energy would be lost in this scenario? 12? So 18 is 12. Now, is the energy really lost, though? No, the energy just was transferred to someone else. Is your money that you lose in Vegas really lost? Did that money else has it now, that's all. Oh, here's the other analogy I gave to students in the first block. You have money in your bank account. You want to go downstairs to the bank machine and take out cash. Are you allowed to take out your cash for free? Or does the bank machine charge you like $3.25 or $4 for your own money? Can you think of a bank fee as being like the inefficiency there? You have $100 in your bank account. But if you wanted to go take out all of your money downstairs right now, would they give you all $100? Or would you get $100 minus $3.25 for the bank fee, right? Does that make sense? That's the inefficiency. That's the fact. Before I get to my example, I think this one goes without. And we're literally wasting money, right? And so that's, I mean, concerns as well. But in general, if we're not being efficient with more. So, okay, we got two examples, and that's it. And these examples, I think you're going to literally dividing two numbers by each other. And it's always little number divide big number. Otherwise, you get more than 100%. So here's the example. A crane, you know, like one of those things it does 2.30 to the 4 joules of mechanical energy input, but it only does 8 to the 3 output. What's its efficiency? So your formula is basically to take your bigger number and which number is bigger, though? As you look at these numbers, you go, 8. 8 is bigger than 2.3. No, because you got to know what this means here. This number right here is really 230,000. We've just written them in a different clear what the accuracy. So another way. So your output was 8,000, and your input was 23. We lost, finger quotes, but joules of energy. This is not very efficient. So 3,000 gives me, and don't forget to times by 100 if you want the percentage. I got this. I got 34.7826%. Why didn't we write these numbers as 23,000 as 8,000? Well, it was so that we knew how many digits to specifically round to. This has 3 sig digs. This has 3 sig digs. So my final answer better have 3 sig digs. There you go. Okay, so 38% or 34.8% efficient machine. That was horrible, right? Very, very inefficient. You guys ever have your parents and they buy new appliances? Have like a tag on the front that has like energy efficient, right? Although it's nice to basically buy the highest energy efficient devices, sometimes they don't. But I mean that's the idea is that hopefully over time that having that device that would be great. possible to have a 101% efficient device? You find a way to make one of those, sign me up. That means you're making free energy. That would be amazing. Is it even possible to get a 100% efficient device? No, because that's what this was. A perpetual motion machine would have been 100% efficient. Rotate, which causes... If it was always 100% efficient, this device would run for forever, wouldn't it? But if it was 99% efficient, then this would then drop down to 98%. Oh yeah, I got one last example, then we're done. Did that make sense? Everybody has what they want written down there? Okay, cool, last one. What we can do is we can kind of change the question a bit. So a device is 15%. It's an input energy of this number right here. Don't forget, this number is really 32000 joules. It was 32,000 joules, just times by 10 4 times. What is 15% efficient based on this? I mean, this is really just like if I told you that you got, say, 73% on a test, and the test was out of 3 times by 50. Do you see how it's flipping it around? So ignore that. All we have to do is take 0.15, because that's 15% divided by 100, and times it by 32,000. Will this number be bigger or smaller than 32,000? Much smaller, yeah. So 15% of 32,000, without me typing it in wrong. I got 4,800. That kind of makes sense. You could have done max capacity 32,000 joules worth of work. And that's what's challenging, by the way, is if I were to ask you what's a joule, I can't just hand you energy. Energy is the single hardest thing probably to put into words that I think exists. I don't know how else to describe energy. It's not a tangible thing in the slightest. But you have 4,800, let's call it joules of energy, out of 32,000. Yeah, you are only 15% efficient, because 48,000 out of 32,000, or sorry, 4,800 out of 32,000 must be 15. That being said, I actually would consider that not to be correct, though. Why isn't writing 4,800 like that probably the best way of writing it? Let's try to round it with more accurate significant digits. This very specifically went to 3 significant digits, but if you were to write this down on paper, the person who reads this number doesn't know whether it was rounded to the hundreds. A slight difference when you're talking about physics and measurement. So maybe a better way of writing it is to write it as 4.80 times 10 to the 3 joules. It's still the same number, but in writing it in this format, this guarantees that we knew that was a 4, we knew that was an 8, and we know that's a 0, but I cannot guarantee this last 0. It might have actually been 4804, and we rounded down. Does that make sense? So that's all I can guarantee, is that I can guarantee the legitimacy and accuracy of the 4, the 8, and the 0. Okay. What questions do you have? Anything? Okay, let me stop the video recording, and then we'll go from there. How long was that? 29 minutes. Perfect.